Welcome to my talk on learning site-specific probing beams for fast mmWave beam alignment. I'm the presenter, Yuqiang. Future wireless systems will increasingly tap into the mmWave spectrum to unlock larger bandwidth. mmWave imposes much harsher propagation conditions so that devices need to leverage highly directional beamforming to achieve viable signal strength. Consider a large codebook V with uniform narrow beams used for data transmission. One way to search for the optimal beam is through beam sweeping, which is adopted by 5G. For instance, the base station can perform an exhaustive search, which would cause large overhead and latency. A hierarchical search can reduce the latency by iteratively narrowing down the search space, but it's more prone to search errors. Context information, such as location, out-of-band information, and vision, can also be used. However, the feedback of context information requires additional standardization support. There are other works that replace V with small site-specific codebooks to reduce the beam sweeping overhead. We consider the beam alignment problem for downlink MISO transmission, where the base station has a large uniform codebook V. For each UE, the goal is to select the beam in V to transmit data and maximize the beamforming gain. We propose that the base station first sweeps a much smaller probing codebook, W, with non-uniform site-specific beams. The UE measures and reports the received power of each beam in W, and the base station predicts the optimal beam according to a beam selection function using the feedback. Since the proposed method only uses the beam sweeping measurements and does not require additional context information, it's compatible with the 5G beam alignment framework. We designed a neural network architecture to jointly learn the probing codebook and the beam selection function. In the offline training phase, the probing codebook W is parameterized with a complex neural network, and the beam selection function F is parameterized with an MLP classifier. The complex neural network module takes the channel vector H as the input and computes the received signal power of each probing beam, denoted by X. The feature vector X is fed into the MLP, which predicts the probability distribution of the optimal beam in V. We train the neural network from end to end to minimize the cross entropy between the predicted distribution and the true optimal beam. The channel vectors can be obtained through ray tracing simulation before deployment or through channel estimation. In an actual base station deployment, the probing codebook is extracted and implemented in RF. The base station periodically sweeps its learned probing codebook W, while the UEs measure and feedback the received power, forming the feature vector X, which is fed into the MLP beam selector. Using the predicted posterior probability from the MLP, the base station can select the optimal narrow beam or the top K candidate beams to try. We can retrain W and F if the environment or the UE distribution changes. In our experiments, we used ray trace channel data in an urban street environment from the public DeepMIMO dataset, containing both line-of-sight and non-line-of-sight UEs. The base station has a 64:1 linear array. The carrier frequency is 28 GHz. V is a 128 beam DFT codebook. For baselines, we consider an exhaustive search that picks the beam in V with the highest received power. We also consider a two-stage hierarchical search with evenly spaced white beams in the first stage. Both search methods are affected by noise. Let's first look at the beam alignment accuracy. With just 6 probing beams and no additional beam sweeping, the proposed method outperforms the hierarchical search. By trying the top 3 candidate beams, the proposed method can even outperform exhaustively searching 128 narrow beams, which is a 14-fold gain in latency. With 12 probing beams, and by searching 3 candidate beams, the proposed method can achieve an accuracy of over 88%. If we consider simultaneous beam alignment for 10 UEs, we incur just 1/3 of the beam sweeping overhead. Next, let's take a closer look at the learned probing codebook. In the environment, there's the metal screen in front of the base station and 2 reflectors on both sides. Looking at the learned beam patterns, we have strong beams pointing towards the line-of-sight UEs or bouncing off the reflectors to reach the non-line-of-sight UEs. Meanwhile, there's little energy directed towards the blockage areas. Remember that we do not explicitly optimize the probing codebook for beamforming gain or SNR. Instead, it's trained jointly with the beam selection function in an end-to-end fashion. Nevertheless, it manages to consistently learn meaningful beam patterns that make sense in the context of the scattering environment. To conclude, we propose a beam alignment method that predicts the optimal beam after sweeping a small probing codebook, which is learned using a neural network and is adapted to capture characteristics of the propagation environment. We show that the proposed method can achieve high beam alignment accuracy, outperforming the hierarchical and even exhaustive beam searches, while reducing the beam sweeping overhead by threefold. That concludes my presentation. Thank you.